Okay, so now that we've introduced angular momentum, just like when we introduced torque, all the formulas in the linear thing about force carries forward. So if there's a first law and second law for force, there's a third law as well, and it's the same thing. You have first law, second law. We won't talk too much about third law on torque. So what is the law that applies to linear momentum? We have the conservation of momentum. Right, so what we will have essentially is we'll have a law of conservation of angular momentum. So what that means is, again, same thing, is if you add up all the initial angular momentum, it will equals to the final angular momentum. So this is will work for a lot of collision problems that has angular momentum as well. But just to give you a conceptual example first, for example, this is a common phenomena that if you see ice skaters do. If you are standing on, so if you sort of ice skating and extend your hands and you try to rotate. Okay. Now the question is, what happens if you if you can stand on a spinning disc, very friction lights or frictionless spinning disc, stand on your hand and rotate around. Okay, what happens if you suddenly pull your hands in? Okay, so the question is, what happens if you're spinning, right, or you're ice skating? So there's a very small friction over here, and you're just spinning around, and now you pull your hands in. Okay, that's not a very graceful position. How do ice skaters do it? Oh yeah, of course, they put it like this. That's much more graceful. Let's remedy that. All right, yeah, a little bit better. Okay, so what happens to their spinning? So if you ever watch, if you've seen that phenomena or have done it yourself, you know that you will speed up. So you will sort of spin much quicker. So why is that? So I'll give you a conceptual example, right? So because the initial angular momentum you have should equals to the final angular momentum you have, right? So what's the initial momentum of the system? So we'll apply it to the system, but the system is just you, your body, right? So let's look at the magnitude. And what changes is the moment of inertia, right? So just on a concept, which one has a larger moment of inertia? So which one's harder to, so I want to find out what happens to this final speed, right? Final angular speed. So the amount of angles, remember this is amount of angles per unit time, your final speed. So let's isolate that, make that the subject. So it's I over IF, like this, all right? So I have this fraction. Let's see if that's larger or smaller than 1. So which one's larger, the initial or the initial moment of inertia or the final moment of inertia? Which one's easier to spin when things are extended out or if it's close to the axis of rotation? This is the axis of rotation, right? So it's much easier this way. So this should be small. Yeah, so this is small, this is large. So what happens to this? So this is large, this is small. So this would be, so if this is whatever number this is, this divided by this, it will be larger than 1. So this is larger than 1, right? So your speed will speed up. So now you understand exactly why if you suddenly pull your hands in, or like that, pull your hands in, you will speed up the rotation like this. A little bit more concretely, right? Let's approximate this gracious ice skater as a rod, because why not? So if this is a rod and you're spinning around the axis like this, so you can look up in the table, I think it's 112 ml square. Yeah, 112, yeah, ml square. So if this is the length of the rod, the moment of inertia is 112 mass times length square, 112. And now notice if you shrink here, so basically you just have a shorter rod, right? So what happened to your length? Little l prime, right? It suddenly decreases. So if I went from, let's see how much it decreases. So this is approximate. That's roughly a meter. That's roughly a meter. So let's say this is roughly 2 meters. Yeah, just very roughly. and say this L initially is 2 meters. And if I shrink it back to here from shoulder to shoulder, if I put my hand here, let's do sort of some estimates as well. It's good for the soul. It's good for applying physics to daily life. That's what I mean. If I do this, so my rod sort of shrink to just 0.5 meters, let's say, right? So half a meter from shoulder to shoulder, roughly, right? So L prime, let's say half a meter. Okay, so how many times did it decrease? That's 4 times decrease, right? So what is I final? What is I over I final? Well, I is proportional to L squared, right? You can see. So if this decreases by 4 times, then the moment of inertia will decrease. It's actually equal, but yeah, if this decreases by 4 times, this will decrease by 4 squared times. So I will decrease by 16 times. Okay, so this will be 16. What does that mean? So the one will be 16 times of the other. Which one's smaller? This one's smaller, right? So sorry, 16 will be here. This is how I figured the proportionality out. So this is larger, so it will be how much larger? 16 times larger than this, or 1 over 16. IF is 1 over 16 of that, right? So I over IF, I over IF is 16, and L will spin 16 times faster. All right, so this is just a quick estimate. So even if you say, hey, I didn't estimate 2 right, all right, so let's say it's somewhere between 10 times to 20 times faster, right? So maybe not as drastic as 20 times, and there's also a little bit of friction. Let's go with a lower estimate of around 10 times. So you see this is a very drastic change. You go 10 times faster. Do I need to worry about the fact that I'm also long, except other than wide? Not really, because if I'm spinning over here, this part you can just approximate. Well, first of all, this part doesn't change, right? So when I'm comparing that doesn't really matter. And also, this is so close to the center, and things that are close to the center that doesn't require that much inertia to spin. It's only when things are far away it takes some energy to spin. Okay, right. So this is a conceptual example. Now, after the interesting part, let's so see, can you apply this to actually make quantitative predictions, which is also interesting, right? It's a good achievement. So here's an example in your book as well. If you have a bullet and shoot that with some velocity and hit a wheel, right? So it's gonna embed in here. And at first, the wheel is at rest. And after you shoot it, it's gonna spin. Okay, so again, we'll draw a before and after. That's usually how the, remember, conservation of momentum problem works. So this is before. I'll probably draw a smaller diagram. After is when they launch to, this is inside the wooden wheel, and this is at rest. And now this guy starts to spin with some angular velocity, all right? So how are we gonna calculate this, right? So we know, let's say we know the velocity over here is it's mass m. Yeah, we're just gonna work with symbols. So this is little m, this is capital M. And we're given radius r naught. And also, yeah, that's it. So we'll see, is kinetic energy conserved, and find out what is the angular velocity. So this is the goal, all right? Let's see if we can find this out. So we'll pick somewhere as the origin. Well, this is going to be our origin, all right? So what is the position vector? So we'll go with before. What's the total angular momentum? Well, we need the angular momentum of the bullet plus the angular momentum of the wheel. Okay. Initial. Now, initial, is this moving? This is not moving, right? It's not spinning. So remember, there's no momentum, or if you look at the magnitude of that, right? That's 0. So the initial wheel momentum is 0. So there's only angular momentum of bullet. You might say, hey, that's not spinning, but we need to look at the system, right? So this is going to be our XY axis. So this is going to be the position, right, R, and this is going to be its momentum. And can you see you have R cross P, right? So you actually have the R of the bullet cross P of the bullet. Let's make it clear for the bullet, like this. All right, so what's the magnitude of this? The magnitude is RP sine theta. What's theta? Well, is it this theta? No, be careful, right? So if this is R, so you want to compare them at the same point. Sorry, that should be parallel. Yeah, so it should be the same as well. So RB. So this is the theta. All right, so you put that in, and yeah, that's one way, but we are not given any information about the theta, right? So let's see if we can use. So that's one way to get it. But since 0 for the wheel, but since we don't know anything about the position and the theta, and do we know P? Well, we're given m and velocity. So what velocity did it? Yes, velocity v. Right. So we're given m, we're given v. So I can claim I know P, but I don't know anything about where it is or the theta or the angle. Okay, so that didn't work. So let's use the other formula, right? So it's also I of the bullet. So this is between. This is also for the bullet, and the omega of the bullet. All right. So the I of the bullet, I know, because that's just a point mass. You can treat that as a point mass. So I for point mass is just mr squared. And I probably need the R. And oh yeah, sorry, no, I have no idea where the R is over here. Okay, so what I do know is if so this is not a good before, because I have no idea where this bullet is initially, right? So let's say before 1 and before 2, and the before 2 is just before it collides. Okay, so the moment just before it collides, so it still has mass m and moving at speed v. Okay, but the wheel is still at rest, right? Just the moment, sort of just before it collides. Okay, so this is the R. These are all the information we're given. Okay, so it's still at rest, so it's just before. So we're going to choose this point instead. All right, so yeah, so same thing, just before the wheel is at rest, so that's going to be 0, and then we have R cross P. Okay, so now this is doable, right? You can use I omega as well, or you can use R cross P. I'll show you both ways work just well. So here the R is R, so the R is pointing this way, right? So this is the R of the bullet. If this is my origin, and this is the momentum of the bullet. So they're actually perpendicular to each other, right? So the I should be drawing it from here, but just want to move it up so you can see. So the momentum's going that way, R is going that way. That's 90 degrees. Okay, so this is just R times P times sine theta, but theta is 90 degrees. So this is really just R times P. I'll put that here just to emphasize, right? So that's 1. And R is R naught, and P is mv, the magnitude of P. I'm given m, I'm given v, right? All right, so that's the initial angular momentum. Good. If you decided, hey, I may have started with this formula, can I do that? Yeah, let's try, right? L of the bullet, I of the bullet, omega of the bullet. So I of the bullet is mass of the bullet times, where's the distance of the bullet from, what is this? This is distance from the rotational axis, right? So distance from the rotational axis, R naught. Okay, so R naught squared, mr squared, right? So that's the I. What's the omega? What's the angular speed of this? Well, I just know the tangential speed, but the tangential speed can be related to the angular speed this way, all right? So if I want this, so that's V over R, and the R is going to be R naught in our case. So we're going to put V over R naught, and it's mass R naught V. And you see, it's exactly the same thing. So they'll both work. Don't worry. It depends on what information you're given. If you're given one, so one of them might be easier, or one of them might be doable. If you're given enough things, both would be doable. Anyway, this is the initial angular momentum, right? Initial, the magnitude of it, taking the magnitude from this step to this step. Here it's still vector, initial. What about final? So final is now the whole thing's moving, right? So the L final, yeah. So again, you can ask, do I know R? So first of all, I have one big thing that is moving. All right. So yeah. So this is L of the, because they're now lodged together. So it's the bullet plus wheel, like this. Okay, so I want to compare the magnitude. Which one's easier? Should I use this or the other one? Let's use this. So I of the bullet plus wheel times omega of the bullet plus wheel. All right. So what's my goal? My goal is to solve for this. All right. So I need to find this. And if I'm given M, V, and R, like I said, and I can probably match these up, right? Initial and final. Okay, so how do I find the I of bullet plus wheel? Well, I of bullet plus wheel is I of bullet plus I of wheel. I of bullet is M R naught squared. And I of wheel is half M R naught squared, right? Capital M, because M of wheel, R naught is the radius of the wheel. Again, this is something you look up. And this is the moment of inertia of that. Right, so can I simplify this a little bit? So I have M plus capital M over 2 R naught squared, right? So that's the combined omega, right? So omega final, let's just call this omega final. And we're done. So if we're given, like I say, if we're given capital M R naught, little m v, and we can now use conservation of angular momentum and match this up just for completeness. You can double check. So if I do initial equals to final, right? Technically the vector, but then if the vector is equals, the magnitude must also equal. So just take the magnitude on both sides. And this side I have M R naught V equals to M plus M over 2 omega F. So for omega F, and you'll be done. See, something can be simplified. Did I miss something? Yes. R naught square. Makes sense. Square omega F, right? So one of the R naughts cancel. So I have MV over M plus M over 2 R naught. Okay, so yeah,